Swayam Prabha. Digital India. Educated India.
Welcome to this module of flow through porous media. We were discussing about immiscible flow. We were particularly talking about this Barclay-Leverett front and how it progresses through a porous medium. So, what we discussed so far is about this Barclay-Leverett front. Here we said that there are two regimes, if you will, of on x axis we can directly now we can start writing it as Vp, that is the pore volumes of injected fluid, which we know in this case is water. So, Vp is the pore volumes of water injected into this porous medium, and on the y axis we write this as Rp, the cumulative. Now, you note here this is not a flow rate, this is cumulative value. So, it is continuously increasing with time. So, at any time this much of pore volume has been injected, that means over this time period, over this t. So, this is a cumulative Vp, and we can call it now the cumulative oil produced is now we call this as Rp. And we said that initially this would be a 45-degree line until the Barclay-Leverett front breaks through at the outlet, and beyond this point this will take a turn and asymptotically reach a limit which is already set based on the residual oil saturation. So, what we note here is after breakthrough of wetting phase, that means after breakthrough of wetting phase means we are talking about this part, beyond this part where it is no longer linear. The total volume of wetting and non-wetting phases produced at the outlet is equal to the volume of wetting phase injected at the inlet. So, that means beyond this point whatever volume is produced that is comprising of both oil as well as water, but till this point it was the produced is only oil, no water, because Barclay-Leverett front has not reached the outlet end till this point. So, here dVp signifies the incremental pore volume of wetting phase injected, that is equal to total incremental pore volume produced. So, dVp signifies the incremental pore volume of water. So, at any point let us say I am looking at dVp. So, dVp injection means dVp production, but these dVp beyond this point is these dVp is comprising of a part which is oil and a part which is water. So, now if there is a fraction means the total dVp I have injected dVp and I have produced dVp, it has to happen, whatever I inject I have to produce. Only injected I inject only water, but produce when it comes to production I produce water and oil. Okay. So, dVp as a fraction, if this is my dVp part, then I can say a part of this dVp is you have as water, and the other part of the dVp is let us say oil. So, this is the dVp. dVp is comprising of oil and water. So, how much would be the non-emitting phase in this case? How much would be the oil? How much would be the water in this produced dVp? That is Fw into dVp, because Fw is Qw divided by Qt. So, Fw into dVp would be the this thing water produced. So, 1 minus Fw into dVp would be the oil produced at this time. So, here now mind it, we already noted that this Fw corresponds to some Sw. Fw, we have looked at Fw Sw curve, and each value of Fw corresponds to some value of Sw, right. They have some relation, and that relation comes from definition of Fw, which is Kr by mu for waiting phase divided by Kr by mu for waiting plus Kr by mu non-waiting, right. That is what Qw by Qt is. And then Kr depends on saturation, there are correlations available. So, we bring in those, and we know that Fw corresponds to some Sw. So, now when it comes to this at the time of breakthrough or beyond this period, we are looking at Sw that is prevailing at the outlet, Sw that is prevailing at the outlet. Now, the cumulative pore volume of non-waiting phase recovered at the outlet, the cumulative pore volume would be Rp is equal to integration of. So, this is basically incremental pore volume of oil produced. So, if you go for instead of in differential form, it would be 0 to Vp, because this is run over dVp. So, 0 to Vp 1 minus Fw into dVp, this is the cumulative pore volume of oil produced. For injection of Vp pore volume of waiting phase at the outlet. So, Vp pore volume of waiting phase at the at the inlet. So, what essentially this whole thing says is, this is the porous medium, we are injecting Qt, which is only water, okay, and then we are producing. So, we are producing here, initially it was only oil, and when Buckley-Leverett front breaks through at the outlet, beyond that point it would carve, it will be producing both oil and water. And cumulative pore volume of oil at any, so suppose I have injected Vp pore volume of water. So, if somebody wants to know how much of oil I have produced against Vp, say I am talking about Vp, which is, let us say, 3 pore volume. So, after injection of 3 pore volume of water, how much of oil I have produced? So, that has to be integration 0 to Vp 1 minus Fw dVp. So, that would be the volume of oil produced. So, this would be the equation for cumulative pore volume of non-waiting phase recovered. Now, if we look at further this expression of Rp, we note that Rp is equal to, we just now said, integral 0 to Vp 1 minus Fw dVp. Okay. So, now we can integrate it by parts. So, integration by parts, take, this is the expression that we already have written, that x is equal to this we already have shown, and this x is basically the distance swept by saturation Sw for Vp pore volume of water injected. This we already have demonstrated in earlier lecture. So, if this is so, if this equation is to be valid, then Sw, a front, will reach the outlet when L is equal to L multiplied by, so that means you are looking at x is equal to L Fw prime Vp. What does this mean? I have a saturation packet, and that saturation packet will travel by a distance x, which is equal to L Fw prime Vp, because of injection of Vp pore volume. So, now we are interested to know when a particular saturation front will reach the outlet. So, when it reaches the outlet, then x becomes equals to L. So, that is why we are saying when this saturation packet will reach the outlet, that is at that time x will be equal to L. So, L is equal to L Fw prime Vp. So, in that case dFw dsW at saturation value, when the waiting phase breaks through at the outlet, that would be equal to 1 by Vp, because here the L and L, they will cancel out. So, basically Fw prime is 1 by Vp. or in other words Vp dFW is equal to dSW. So, one can show from this expression that when this saturation front breaks through at the outlet, at that time dFW dSW at that saturation value when the wetting phase breaks through at the outlet is equal to 1 by Vp. So, this is one thing we must keep in mind, and further we note here that this is Rp is equal to this expression, right. So, out of that 1 minus Fw into Vp, this remains as it is here, and this part Vp dFw integration 0 to Vp. So, Vp dFw is equal to dSw, we have already seen here. So, this goes here. So, instead of Vp dFw, this goes here. So, instead of Vp dFw, we are writing dSw. So, this will change from SWI, which is the interstitial saturation, to the given value of SW. So, this becomes equal to 1 minus Fw Vp plus SW minus SWI. So, this is the pore volumes of oil produced. So, this is given by this quantity 1 minus Fw Vp plus SW minus SWI. This is the cumulative oil produced. Now, if we look at quickly define SW bar, that is average saturation of wetting phase at time t. What does this mean? We said that this is the core, and when we plotted the saturation, we know if Buckley-Leverett front is here. So, then this part. If somebody wants to find out what is the SW bar in this case, what is the average saturation of water as far as this particular part where Buckley-Leverett front has already travelled. If somebody wants to know what is the SW bar, what is the average saturation? So, that value is here. So, that value is most possibly this value will come to something like this, because at this end it is 1 minus SOR, and here it is something less, and here it is SWI. So, this particular level I can think of, which is an integral average of this saturation, which is changing from 1 minus SOR to something below. So, this value is SW bar. So, SW bar is the saturation on the Buckley-Leverett front. So, when the front reaches the outlet, so this is x equal to L. So, this is x equal to L. The front has reached the outlet. So, at that time what is SW bar? Let us say this is the value of SW bar. Here we have SWI somewhere, here we have 1 minus SOR. So, now and SW is the saturation at the outlet phase at the same time. So, this value is, let us say, SW, the saturation at the outlet phase, because here it is SW and here it is 1 minus SOR. So, in between the saturation changes. So, we can have an average saturation which is given by this. So, this SW bar minus. So, now we look at here the Rp, cumulative volume of oil produced, they are writing it as SW bar minus SWI. Why? Because initially how much of water was present in the system? That is the interstitial water saturation. So, if the total pore volume is 1, out of that SWI pore volume of water was present in the system. And at some time t, when this front has reached and this at the outlet the value saturation is SW, at that time the average saturation, these average are nowhere the saturation profile exists, but I have to draw that integral average. So, if we draw that integral average, that average saturation happened to be SW bar. So, at that time how much of water is present in the system? That is equal to SW bar pore volume, right. So, at this time it is SW bar pore volume of water is present in the system, and earlier SWI pore volume of water was present in the system. So, now if we subtract SW bar minus SWI, so that gives me that earlier I have much less pore volume of water present, now I have SW bar which is a larger pore volume of water present. So, where is this difference coming from? This difference is coming because I have already produced some oil, I have already pushed out some oil by injecting water. So, the average saturation for this core, average saturation for this porous plug has gone up. Earlier, to start with, at t equal to 0, this was SWI, and at this time this is SW bar. So, these difference is arising. So, this pore volume difference is arising because this part of the pore volume of oil has been displaced. So, then what is the total pore volume of oil produced? That is simply SW bar minus SWI. So, pore volume of non-wetting phase produced till time t. So, at any time, let us say at some other time I can find this being this part is remain same. Let us say this is the curve or this is the curve. So, then we have to find out what is the corresponding SW bar, what is this difference SW bar minus SWI, and that difference arises because that much of oil has been pushed out from the core. So, that is why produced oil, pore volume of produced oil is SW bar minus SWI. And we have noted earlier that RP, just in the earlier slide we have shown that RP is equal to 1 minus FW into Vp plus SW minus SWI. So, in this case, if we now equate instead of RP the left hand side, if we bring in SW bar minus SWI on the left hand side and right hand side remains as it is, then we get here SW bar is equal to SW plus 1 minus FW by FW prime, or in other words, I mean it is just simple sum manipulation. We see here that FW prime is equal to 1 minus FW divided by SW bar minus SW. So, this is an expression we get for FW prime. So, let me recapitulate quickly what we are talking about here. Number 1, we now defined a concept called SW bar, which is the average saturation existing over the pore space. So, initially truly I have SWI everywhere, interstitial water saturation, but when I continuously injected water, I created a saturation profile, but there is, so I can always get an integral average of that and I can find out what is the average saturation this represents. Some part is above that value, some part is lower the value, but average saturation as far as this entire length is concerned is SW bar. So, this SW bar is going to be an important term for me. SW bar is the average saturation of water inside the pore. And at the same time, we are talking about a term, we are having a term which is SW, we are carrying it here in this factor also. What is SW? SW is the saturation at the outlet. If you look at what was the definition when we arrived at this expression for RP, when we arrived at this expression for RP in the earlier slide, there we had used this part Vp dFW is equal to dSW, this has gone in there to, so that is why we have this SW minus SWI for RP. And how do we arrive at this Vp dFW dSW? That we arrived at by writing x equal to L. Why am I writing x equal to L? What was x? The x was distance swept by saturation SW for Vp pore volume of water injected. So, Vp pore volume of water was injected. I have the core, Vp pore volume of water was injected. And we are trying to locate how far SW front will travel. But now we have insisted SW will reach the outlet when L is equal to LFW prime Vp. So, this Vp and these Fw prime, these they are just tied. There is another additional condition in place. What is that condition? That after Vp pore volume of injection, this is I am assuming that the Buckley-Leverett front has broke through at the outlet. Buckley-Leverett front has broke through at the outlet, and this, when it breaks through at the outlet, this saturation is SW. That has to happen here, because this x is the distance swayed by saturation SW, and we are setting this x as L. So, this SW has reached x equal to L. So, we are talking about that condition. So, so that means when we are talking about SW bar on one hand, which is the average saturation, but at the same time we must remember that the saturation at the outlet, that has to be, that is basically the SW in this equation. This is not any arbitrary saturation value somewhere in between. This SW is the SW at the outlet, and SW bar is the average saturation. So, from 1 minus SOR to SW here, 1 minus SOR to SW, this change that happens, the average saturation here is SW. So, in fact, so because of this reason, I prefer to, we should be writing this SW. Very soon we will see that this SW will be changed to SWF. That means SW of the front. So, Buckley-Leverett front has reached x equal to L, and that saturation there, because we have, you can see this saturation profile, it takes a shape like this. This is SWI, but here this is higher than SW, because this is because of the way the FW curve is. FW curve, had it been in some other form, I mean you can see this is the FW curve. If FW curve is this way, so then probably the tangents and all they were different. So, now these I will show that in a moment, don't bother about this part, but here this saturation here, when it breaks through here at x equal to L, we call this as SWF, to differentiate this from any other saturation value. So, SW would be any individual saturation values, and SW bar would be simply the average of these saturations. So, that is something which we are heading to. So, I will continue this in the next lecture, because our original aim is to predict the how the oil produced and water injected, or non-wetting phase produced versus wetting phase injected, how we can predict the part beyond breakthrough, and when the breakthrough takes place, and what would be the saturation profile over the length. So, these are some of the answers we need to get out of this exercise. So, that is all I have for this lecture. Thank you.